In this tutorial, we're going to look at bits and bytes and the process of binary encoding, which is covered near the beginning of Chapter 2. We touched on this subject near the end of Chapter 1 when we dealt with the principles of new media. The first principle, the principle of numerical representation, states that every product of human creativity when entered into a computer becomes a series of zeros and ones. And to the computer, this is how human communication systems, human input, human products of creativity are expressed. Well, the idea for this is nothing new. A binary communication system that you may be familiar with if you've watched any Western movies is the telegraph, and using Morse code invented by Samuel Morse. Morse code also used two characters. Rather than zeros and ones, it used dots and dashes. The telegraph key that's pictured before you was nothing more than a switch. Electricity would flow through the switch. When the telegraph operator would depress the key, it would complete the circuit, momentarily sending bursts of electrical energy across a copper wire from one location to another. Depressing the key for just a moment would produce a dot or a short burst of electricity. Producing the key a little longer would produce a dash or a longer burst or pulse of electricity. A trained telegraph operator could take letters and words and sentences and very quickly translate those into electrical pulses of energy that would travel across a copper wire from one location to the other, encoding human language into dots and dashes, and a telegraph operator on the receiving end of that communication would reverse the process by decoding the dots and the dashes back into letters and words. So this process of binary encoding really has two parts: the sending part, which involves encoding, and the receiving part, which involves decoding and reconstituting the message on the other end. A computer does this for us much faster than a human telegraph operator ever could. To give you an idea how this works, in this system, we can zoom in and you can see the letters of the human alphabet, the English alphabet anyway, are represented by their Morse code equivalents. Thus the capital letter A is translated into a dot followed by a dash. The capital letter B is a dash followed by three dots. And the capital letter C is a dash, dot, dash, dot. Every letter in the English alphabet has a Morse code equivalent that a telegraph operator would be familiar with, along with punctuation marks and numbers. To see this in a slightly different light, let's jump over to the web. I've searched for a Morse code translator using the Google search engine, and I found a translator that allows me to enter in English text in one field while translating it into Morse code in the output field. In the input field, I've typed hello, and in the output field, the Morse code translator has given me this series of dots and dashes representing that word in Morse code. Well, we don't always have simple one-word sentences to communicate. What if I type in something longer, like the First Amendment to the U.S. Constitution? Well, this is a longer phrase. It's probably going to require a great deal more dots and dashes. We'll translate this, and just as quick as that, the Morse code translator shows us what this would look like in machine code. And this really is machine code translated by human telegraph operators as they would have done so back when the telegraph was in full swing as a human method of communicating. But again, this is a binary communication system. This process and this idea is not new, but it's given new meaning in the digital age of computers, where the computer converts human language and the products of human creativity into zeros and ones. For a second example, let me go to another website. This is one I found that actually converts or translates English language text into ASCII to binary code. So in this example, I've typed in the phrase smiley face, similar to what I did in Chapter 2 in the text, and output it to binary code on the right. And you can see, again, a string of zeros and ones on the right-hand side representing the 11 characters in the phrase smiley face. Well, again, to make this a little bit more complex, let's type in our phrase from the U.S. Constitution, the First Amendment, click on to binary, and you can see more effort went into this, although the computer did it very, very fast, but lots and lots of zeros and ones needed to represent a longer section of words from the human language. For one final glimpse into the world of binary code, let's jump over to a program that I've downloaded to my computer called Hex Editor. I've opened up an image, this file called bluesky.jpg, and over here on the right hand side of the screen, my HexEdit program shows me visually what this looks like to the computer in hexadecimal and binary format. Now this is very complex and I don't have a lot of time to explain what all is going on here. I'm not quite sure I totally understand, but as we scroll down you can see lots of information. What you're looking at here is the digital information that is in the file for this digital photograph, the bluesky.jpg file image. This is what the computer sees and this is how it interacts with it. Now contrary to that, we have another file that I've opened up, and this is the text file containing smiley face, our 11 characters, a simple phrase made up of 11 letters of the alphabet. And again, you can see that the binary representation is much less complex. In fact, it's only made up of 11 bytes, whereas the image file on the right is 5 million bytes of information. Well, this is enough right now for binary data. I think we've made the point that when you work with a computer, that the files that you have to manage on a day in and day out basis are nothing more than numerical representations of what you see on the screen or what you hear through the sound card of a computer. It's all translated through this process of encoding and decoding, and the computer is able to do this process very, very fast.